Welcome back to another LeetCode problem. We're going to have a look at a medium problem called diagonal traverse, LeetCode 1424. We are given a 2D integer array of numbers, and we're supposed to return all of the elements in nums, but in diagonal order, as shown in the images below. So not row order, not column order, but in diagonal order, like so. In terms of constraints, we have, there's some constraints on the values that are inside the array. I don't know why that would interest us much, because we're using Python, we don't care. And, for how large these numbers are or how small they are. But what is interesting is that, the length of individual rows can be different for each row. And which means we'll have gaps here. And because it's a medium problem, it's very likely that, if we pretend that the whole array is filled to the brim, we're probably going to end up with a solution that's not going to be very effective, or might even get rejected because of time limit exceeded. And yes, so for our analysis, we're going to pretend that there are no limits on the number of elements in the array. Otherwise, everything is constant space and constant time. I think we could implement this diagonal traversal over all elements right away. And that might be the easiest one. So let's just try this and see what LeetCode says to that. So we would iterate over all of the elements. And so we have to take into account how many elements we have, but also how wide and how tall it is. Because if we traverse, if we want to go through the diagonal that goes through this 9, we have to start somewhere here. So it's twice the height of the array where we have to start in terms of y position. And so we will have a runtime complexity of width times height of the array. But it's really 2 times width and 2 times height. And of course, and time and space complexity. Because m is height. Because, in the worst case, the whole 2-dimensional array is filled to the brim. And then we have to add all of these m width times height number of elements into our return array. Cool. So yeah, let's just do that. So we're just going to extract the width and the height. So the height is going to be easy. So that's just going to be the length of the nums. That's the number of rows we have in there. And the width, well, we don't know where the maximum row is, right? So we have to find it somehow. And we're just going to iterate over all of the rows and determine each row's length for row and nums. Right, there you go. I think they should have named this grid instead of nums, but nobody's listening to me. So we'll deal with that. Okay, cool. So now what we do is we just iterate through the diagonal. So this would be the first diagonal, the second, the third, and the fourth, fifth. And then for each diagonal, we're going to iterate over all of the values that lie on that diagonal. And this is also something that comes up in several LeetCode problems. And for diagonal in range, well, we start at 0, and we already determined that we have to, we have to hit the 9, but we also have to hit the first element down here and the last element that's potentially here. Maybe this is the longest row, so we have to hit it. So the range will be, the maximum will be the sum of width and height plus height. So that way we make sure that we capture the diagonal tip as well as the maximum element in a row or whatever. Wait, yeah. No, this is purely to capture the diagonal tip. That's why we need that here. Yes, that's why we need that. Not because of the last element of the row or whatever. Cool. So now, as you can see, we have, every time we start with an x coordinate that is equal to 0, and we start with a y coordinate that is equal to the diagonal, right? So that'll be 0 and diagonal. So yeah, so if we start here, that means we're at x0, but at y2. So 1, 0, 1, 2, the second diagonal. There we go. And now what we do is we just iterate as long as y is larger than 0. So we iterate from the bottom, from the left bottom corner to the top right corner on this diagonal. And well, we have to check, because we're going beyond the height, we have to check if y is smaller than the height. If it isn't, then there's nothing for us to be found there. And then we can say, okay, we're going to extract the row, and that is in the in row number y. And now we also have to check if actually our x is still smaller than the length of the row, because all rows can have different lengths. So if we add this diagonal here at 14, then we go here, we need to check if this x actually exists. And this is how we do that. And then basically we append the cell value. And we have to keep a result array here. We have to append that value to our result. And that'll be row at position x. And then, so that we don't run into an infinite loop, we have to increment the x, and we have to decrement the y. And this is equal to moving one step up on the diagonal. That's what that is. Yeah, and then finally, we return the result. And that looks good to me. So let's just run this test. Nice. And it works for both of the test cases. So if I submit this, let's see what happens. Okay, this is already running kind of long. And we get a time limit exceeded. So that is a hint that our solution might be correct, but it's just too slow. Otherwise, we would have probably gotten an error. So yeah, so how can we improve this? Well, we have to exploit the fact that some of these cells don't even exist. And and something we could do is, maybe we can identify numbers that are on the same diagonal, because we know that the first number in the first row is on the 0th diagonal, then comes the second and third diagonal. So we can do that, and we can do that for every row. We can determine, okay, to which diagonal does this number belong, right? And we know that in the row number 1, so we are index is 0, so row number 2 at index 1, that first element doesn't belong to to diagonal 0, but to diagonal 0 plus 1, and so forth. So we could do something like that, right? So we iterate over all of the rows, and for every element in the row, we can assign it a diagonal. And we also know, because we are iterating from the top to the bottom over the rows, if we were to keep like maybe a queue of all the elements that are in that row, we know that these elements would already be sorted. Meaning the last element in the zeros in the diagonal 1 is the first one to be popped out. So that's the 4. And then the 2. So we could group all these values together into diagonals and into their positions. We could do that, but that would increase our... What would that do for us? Well, it would do for us that we are reducing our runtime and space complexity by however many cells are empty. So maybe we should just try this. And if that doesn't work, maybe we have to try to find another optimization. So let's just do that. So for row, well, for y, row in enumerate nums. So we're iterating over all of the rows. And now the diagonal is equal to y, right? So actually we could just place this like that. So Yes, and now we iterate over for the YAG value in enumerate row, and we say start is the YAG value. So we take this value as the starting value for this. So now what we have is we get actually the diagonal into which this value belongs, right? So if we do this, let's use a default dictionary just for convenience. From collections, import default dict. And by default, it's going to create a list of elements. So we're just going to append diagonals, diag append value. Right. And now, finally, what we do is we just iterate over all of the diagonals. For diag, well, actually, let's see. Diag, we start with 0, while diag in diagonals. Because I don't know if we iterate over the keys of the dictionary, if that's going to be in sorted order. But we know that we start with diagonal 0, and we're going to iterate while we have those values. So, and then into our result, we're going to append the diagonals at diag, but we need to reverse it, right? Because we added them in reverse order. And it's not append, it's extend. Yeah, I think that should work. So let's give it a try. Aha. Typo. Let's try again. Of course, same typo. Let's try again. Okay, this is also running quite long. Time limit exceeded. Okay. Yeah, of course, because we're not incrementing our diag value. I've been doing too many LeetCode problems today. That's why my brain isn't functioning as well as it did earlier. So, okay, so this works. And yeah, let's put it to the test. Let's see if that one is faster. Oh, first let's do time space complexity analysis. And actually now, n is the number of in our nums array. So let's submit that. Oh, and there we go. So that seems to work just fine. Very nice. Let's see, can we optimize this even further? So if of n time and space, that's very good. Is there a way of how we can actually change that with the space? Well, if we could encode the position of a number inside the existing nums array somehow, then we could probably sort it. So then we would go to n log n time, and because sorting in Python is in place and constant space. How could we do that? It's not that easy, is it? It's not that easy. But I'm not going to implement this, but here's an idea that you can try. Well, you could argue that, well, you just need to have an order. Well, you have to have the diagonal, right? So you need to take into account the current diagonal and the current length of the diagonal array, so of that you have at that point. And that length has an upper bound, right? because you know that per diagonal you can have at most, so in diagonal 0 you have one element at most, and diagonal, sorry, in diagonal 0 you have at most one, at diagonal 1 you have at most two, etc. But the maximum diagonal, I think, is width times height, isn't it? Width times height. So if you did that, diagonal plus x times something like that, you could probably, encode the position with some logic like this. There's probably an error in here, but something like that. And then you can exploit the fact that you know that the numbers are all positive and that they are bounded. So then you would probably just, add, let's say, to the value in nums at whatever that position is. You just add a certain value to it. Maybe 1000 times, whatever this Z value is that you came up with. And then you can just sort the entire nums array. And then you just reverse, or you just remove the part from the numbers that is larger than that. So you would, in the final pass, you would just iterate over all of the nums. Nums at position I equals nums at position I. And then, well, you just have to cut off the higher bits, right? That's basically what you have to do. So you would probably do some, I don't know, you can do some bit masking, right? And then you have, I don't know, whatever number you need to have to match all of the bits of 10 to the 5th, right? So that's how you could do that with a little bit of bit masking and reusing the nums array. But the difficult part is to get this number, this ordering number, correct. So I don't want to do this now because I know this is going to be complicated. And unless you have done this before, you're probably not going to be able to reproduce this in a interview setting. So yeah, anyways, so that's it. Have fun. I hope you practice this one as well. Try both implementations, try to explain the trade-offs between the two. And yeah, just practice interviews.